This week, we want to look at three different distributions that are particularly important. On one hand, we have two discrete distributions, namely the hypergeometric distribution and the binomial distribution, and then the most important, continuous distribution, which is the Gaussian normal distribution. We'll also see again next week, in relation to the central limit theorem, why this distribution is so special. All right, before we can start with the continuous distributions of the hypergeometric and binomial distributions, we need to establish a certain foundation, and we need to introduce the binomial coefficient, and that's exactly what we want to do in this video. And for that, we'll take an example, namely the example of three numbers. And we ask ourselves, which is the typical example of a binomial coefficient, how many combinations of three numbers are there when playing the lottery? When playing the lottery, if you haven't done it yet, there are 49 numbers, and you have to mark 6 numbers. So you have to take 6 different ones, and the order doesn't matter. So there are different numbers, and each number can only appear once, and 6 numbers are drawn. And as I said, the order in which you choose these numbers can't be tracked, so it doesn't matter. And now we want to gradually understand how many possibilities there are here. So let's first consider what it would be like if the order did matter. So how many possibilities would we have if the order did matter? And then it would be the case that we would have 49 possibilities for the first number to draw a number from 1 to 49. And then the trick is that while the order doesn't matter, we can't pick the same twice. So for the second number, there are 48 possibilities. For the third, 47, 46, and so on. And the number of possibilities is the product of all these options. So we get 49 times, 48 times, 47 times, 46 times, 45 times, 44. And so this is the number of possibilities when the order does matter. And now we need to think about how many of these combinations have the same order. Determine how many ways to permute 6 numbers. It's 6 factorial, 6 options, then 5, 4, 3, 2, 1. I get all combinations by dividing 49 times 44 by 6 factorial. And you know this too, it's 6 factorial. For the first position, you have 6 options, then 5, then 4, then 3, then 2, and then 1. And then you already have the result. Because when you consider these 6 numbers with their order possibilities, each arrangement is actually seen as identical since they just have a different order. So I get all the combinations by dividing 49 times 44 by 6 factorial. And that's this expression here, yes. And what you can do now is rewrite the expression a bit differently. You can write 49 factorial, but then you've written a bit too much in the numerator. No, what have you written too much? Well, all the way down to 43, 42, and so on. They don't come into play anymore. So we divide by 43 factorial so that all these numbers cancel out. All numbers from 43 onward. So we have, so to speak, this means that this here corresponds to 49 factorial divided by 43 factorial. Well, and the other part, 6 times 5 times 4 times 3, is 6 factorial. That's the result. And we call this number the binomial coefficient. So we write that down in this way here. So we write a 49, then a 6 underneath it, and we put the whole thing in big brackets. Without a fraction line or anything like that, we just write the numbers one on top of the other. And we call that the binomial coefficient. And we can do that quite generally now. So we can call this important number the binomial coefficient. So if we have two numbers, n and k, natural numbers, where n is greater than or equal to k, 0 is also allowed. I can say again how we deal with 0, but then the binomial coefficient n over k is defined as n factorial divided by n minus k factorial. So that was the first part. So that's the number of possibilities, taking the order into account. And then we divide by k factorial again, to disregard the order. And of course we can also write that as this product here. That would be the other way of writing it. So just to clarify, this n factorial divided by n minus k factorial is basically n times n minus 1 down to n minus k plus 1. That's this part. And this k factorial part is then this part here. Alright? Also we say n over 0, which isn't entirely clear how that's supposed to be defined. That's just 1 with the idea that we have one way to choose 0 elements from n elements. Yes, exactly. Exactly. So maybe let's clarify what that means now. So the interpretation of n over k is the number of ways to choose k different elements from n elements, where the k are all distinct and the order, as mentioned, doesn't matter. Just like you saw in the lottery. Alright, and exactly, so we call that n over k, or also k out of n. Both ways, common, so when we talk about it. Okay, now there are two important identities for the binomial coefficient. On one hand, 1 over n is n. We can briefly think about how many ways there are to choose one element from a collection of n elements, n pieces. We can basically take 1 out of the n each time. N over n, so how many ways are there to choose n elements from a set of n elements? Well, there's just one, so that's identical to n over 0. So that means, sorry, I'll write that down again really quickly. So that means that this here is equal to 1. And it's interesting. Let's take another look at that. How many ways are there to draw elements from n? Well, you can also look at it this way, that we're not taking them out, but rather considering how many possibilities there are for elements to remain. So in the lottery, for example, you can say that choosing 6 out of 49 is the same as choosing 43 out of 49, and the 6 are the ones that remain. That's of course the same 2001. The same number of possibilities, but from a different perspective. And that's basically what this formula here states. Exactly. And then there's another very, very important one. Namely, this one, this identity. And that says that there is a connection between n1 over k1, sos ios, n over k, and n over k. First, we're not going to do that in this video. We might discuss why that is in the lecture later. This identity helps us determine what's called Pascal's triangle. So we write down the following triangle, where at the top we have 0, choose 0, 1, choose 0 over 0, 0, choose 1 over 0, and 1, choose 1. And you can see then we always start going down here successively. And if we plug in the numbers for this triangle, then we see the following. And then you see the following identity. Namely, if we take a number out here, like 10, for example, then that's the sum of this here, plus this here. And exactly, or for example, this whole thing here is then 20, which is the sum of this here plus that one. And so you see that you can actually determine all the binomial coefficients recursively by calculating them. step by step from the upper rows. That's a very nice formula. It's called Pascal's triangle, and as I said, it is based on the formula we saw here, that I can look at n-1, choose k-1, so to speak, as the sum of the n-1 row from the nth row. All right? And then the last identity, which is called the binomial coefficient. And there's a reason why it's called the binomial coefficient. It's because it has something to do with the binomial formula. And I just want to show you a quick example of that. And we're going to take a look at this series here, for example. Let's take a look at this series here. So we're now looking at the, well, if we count that, the sixth row actually. Why the sixth? Because this is the 0th, 1st, 2nd, 3rd, 4th, 5th, 6th. Yes, we start at 0. And these numbers that are in the 6th row, that's the beautiful connection. Those are the coefficients of the formula x plus y to the 6th power, namely 1 times x plus 6 times x to the 5th y, 1520, 1506 first. And just to make that clear again, here is the 1, here is the 6, here is the 1520, 1506, and 1506,000. Here would be the 1 again. And those are exactly the numbers that are in this row. Yes, that means it's also a very nice interpretation. So, binomial coefficients are the coefficients of the binomial formula that appear here. Okay, so those are binomial coefficients. Just a quick overview, and as I said, we need the binomial coefficients for our two distributions. The hypergeometric distribution, and as the name suggests, the binomial distribution. And in the next video, we'll take a look at what the hypergeometric distribution is. Until then, take care.